Hello, my name is Dmitry. I'm going to present our work on repairing brackets, which is joined with Mikhail Vyalyi from Moscow. This is the outline of the talk, where item 1 corresponds to the motivation, why we do something, and then number 2 corresponds to the main contribution, which is something called the repairing problem, which is introduced in this work. So before I talk about the actual motivation, the specific paric images of one-counter languages, let me give you the context. The context is something called state complexity, and even more broadly, this is program size complexity of problems. In general, this is the minimum size of programs that solves a particular problem. And here in formal languages, if you think about a formal language L, then you can think of the minimum size of an automaton, say NFA, that accepts this formal language L. Why do you care about this minimum size? Why do you care about these measures? Well, there are three broad reasons. So first of all, if you think about how to prove lower bounds for state complexity, or more generally program size complexity, then these lower bounds correspond to arguments showing that no machine can solve a problem efficiently. So this is about understanding what makes problems difficult, a general quest in theoretical computer science. The other two motivations are that these days, especially in verifications, as we give programs and their models to other tools, SMT solvers, model checkers, whatnot, the smaller the programs are, the faster the tools in principle can work, hence minimization questions. So finally, if you prove lower bounds on state complexity or program size complexity, you uncover limitations of models of computation. And limitations can then be transferred into analysis algorithms. So in this talk, my motivation is primarily item 1 in this list. So the specific setting in which we are going to discuss this is something called paric images. So, and this is a classic instrument in formal languages. So suppose you've got a finite alphabet sigma, shown here, from composed of R letters, and then you've got a language over this alphabet, L. Now consider the set of all R-dimensional vectors, M1 through MR, such that each component of this vector counts how many times each letter occurs in the word. So put different, for each word over this alphabet, count how many times each letter occurred. For example, look at line 1 here. There is this word AA, BB, BBA. So it has 3 A's and 4 B's. So therefore, the paric image of this word is 3, 4. Now, if you've got a language, you can count that for all letters, and this way you get the paric image, or the commutative image, of the language. So here are two languages, one regular and one context-free, that have the same paric image. So the paric image was proposed by Rohit Parikh at the beginning of the 1960s, at the outset of formal language theory. And here is a theorem that I formulate in a modern way due to Esparza, Kiefer, Ganti, and Luttenberger. So for every context-free grammar, there exists a non-deterministic finite automaton that has such that the languages of this grammar and of this automaton have the same paric image. So these two languages are paric equivalent, or you can say that the grammar and the automaton are paric equivalent. So in Parikh's original work in JACM 1966, there were no bounds of this form given on the size, and the specific setting, these specific numbers, are due to Esparza et al. In particular, they tell you that if you've got a grammar with, let's say, n non-terminals, then there is a paric equivalent NFA of at most an exponential size. So this is 4 to the size of the grammar, and you can think of this as the grammar given in Chomsky normal form. So why these numbers, and why care about these numbers? Well, Parikh's theorem is used in software verification in multiple contexts and is a very basic tool where representations as non-deterministic finite automaton are useful, which is why these numbers are important. So this is an exponential upper bound, but in fact you cannot do much better than that in general. If you have a doubling grammar that just has n simple non-terminals, you can find a grammar that generates an exponentially long word and only that word. And then if you want to construct an automaton that accepts exactly the same singleton language, this automaton must have to be exponentially big. So somehow the exponential here in the theorem, you can't really improve this to below exponential. But then you can ask what happens if you look at subsets of context-free languages. What happens if you look at one-counter languages? Well, the upper bound remains valid, but for this subclass, this lower bound fails. So, and then the lower bound is polynomial and the upper bound is exponential. Well, you should ask why care about this question. I mean, you can consider all kinds of stuff. Well, let me show you a particular motivation for this problem. So, and this is something called availability languages due to Honecker, Meyer, and Olderhog. So they are basically an advanced version of regular expressions. So take usual regular expressions and add the following feature. Suppose you have an additional symbol in your syntax called this check mark, and then you can put some sub-expressions inside parentheses and impose constraints on these sub-expressions. And then the semantics means that among all the words that are generated by this sub-expression, you only keep those where each prefix ending with this check mark satisfies a constraint. So, and you can think of these constraints as having linear equalities and linear inequalities on the number of occurrences of these letters. So let me give you an example. So start with this expression in the middle. You have A star, B star, C star, and then you have a check mark. Now you put that into parentheses, and then you require that the number of A's is at least the number of B's. Okay, so then you get rid of some of the words. Then you put another check mark, and then you put another constraint. So now with these two constraints, what you get is this language. Obviously, reasoning in this way, you get languages that are obviously not context-free. So these availability languages are motivated by verification question, and language emptiness, just checking whether a given expression generates at least one word. This question is not very easy, so it's shown that it's decidable in non-elementary time, so this is a tower of exponents. But then this construction really uses the Parik image of one-counter languages. So what it does is it constructs an automaton that kind of keeps track of the difference between the sides in this constraint, and then you only keep track of the Parik image. Now what happens is there is this exponential construction for Parik images that for context-free languages, and then in principle a big expression can have many nested constraints, and then you kind of have this exponential iterated, which is how you get to tower. So if for the question of converting one-counter languages to Parik images of to Parik equivalent NFA, if you get upper bounds that are sub-exponential, then you get better results than this tower. You get something like elementary, so doubly or triply exponential, depending on the specific function. So this is why NFA for NFA Parik equivalent to one-counter languages are important. So what are these one-counter automata precisely? So they're push-down automata with exactly one non-bottom stack symbol, meaning that you can distinguish between the bottom of the stack and non-bottom of the stack, but that's it. So effectively you have a counter that takes non-negative integer values and that you can check for 0 or non-zero, but you can't distinguish between different positive numbers. So in this simple example, you have 3 control states, and you start in this control state with counter value 0, and then you can have several A's, each time incrementing the counter. Then you transition non-deterministically to the state Q, and then you can read several B's, decrementing the counter. But you won't be able to read more B's than A's, it's just that this transition won't be enabled. So then, if the final transition checks for 0, then you really have A to the M, B to the M. So the language of such an automaton is a set of all accepted words. So, and such languages are called one-counter languages. Now, one-counter languages sit between regular and context-free, and this A to the M, B to the M is one counter but not regular, but then WW reverse is context-free but not one counter. So this is really, these inclusions are both strict. So reasoning about one-counter automata is quite difficult. So Leslie Vyalyi proved in the 1970s that universality is undecidable, meaning checking that all finite words are accepted. But at the same time, in the deterministic case, language equivalence can be decided in polynomial space due to Valiant and Patterson. And it took 40 years before Birngeller and Janchar showed that, in fact, language equivalence is in NL, so NL complete. But most importantly for our work, shortest accepted words by one-counter automata have polynomial length. We proved a couple of years ago that they are actually at most quadratic, but this is not important for this work. So what's important here is that this exponentially long example that witnessed the lower bound for the context-free grammars to paraequivalent NFA conversion, that this exponential lower bound kind of vanishes completely. So really the question is how to find a better upper bound. So, and in fact, this is something that's possible. And a few years ago, a big team in which I was honorably included by Fauzi Atik, Piotr Hoffman, Georg Zeche, Kumar, and Prakash Saivasan, we proved that, in fact, if you start with the one-counter automaton with n states, then you can find an NFA of size n power log n that is paraequivalent to the initial one-counter automaton. So this is a function that grows much slower than 2 to the n or 4 to the n. This is basically 2 to the power log squared n. So this is a quasi-polynomial construction, and it significantly improves the upper bounds on these availability languages that I showed you previously. So in fact, if the input alphabet is finite, then you can improve this to polynomial, so n power big O of 1. But if the alphabet size grows, then this was the best that we could do, and the question is, can you get this further down to polynomial? And in this work, in this year's LICS, what we showed with Mikhail is, in fact, there is a lower bound that is higher than polynomial. This is n power something that's roughly square root of log n. So this log n is really tiny, so this is basically n power square root. So you can't have a polynomial translation here. So this is the main result. So let me tell you now how we get here, because this is a very non-trivial statement. So in this work, for years ago, a part of the result was a hard example. An automaton that looked something like this. I'm simplifying it slightly. So look at this following way. You can start in the state, and this is the only final state. You can have loops that alternate signs. Here you add +1, here you add -1, and then you can go left to right. So now each transition has an individual letter. So you record how many times you've looped in each state, and then all transition, and you kind of in using these different input symbols, you kind of record in the input word which subset of the states you visited. And you can show that this is the hardest example, or well, a variant of this language is the hardest example, meaning that if you can have a polynomial translation for this OCA, then you can have a polynomial translation for all OCA. So this is really kind of complete or hard language. So now, how do you show lower bound for these OCA? And this is something that we do in this work. So, and this is what this repairing problem is all about. So let me tell you it in an abstract way. So it is defined for Duke words, so balanced parentheses, but since we're talking about one-counter automata, let me instead use pluses and minuses. So I'm really not repairing brackets, I'm repairing signs. So now let's define a following one-player game. So in a move, so I can erase any pair of plus and minus such that plus is to the left of the minus. For example, I can remove this pair, and then this, and then, well, this pair, and the goal is to erase everything. Okay, now I've reached my goal, but then I can do this in multiple ways, so I can define the cost of a play. So the cost, well, the objective is to minimize the width, and the width is the number of islands of signs separated by blank space. So let me illustrate this. So here I've got one big blob, one big sequence of signs, and it has width 1. So after I remove this block, well, my width is 2 because there is one block on the left and one block here on the right. Now this keeps the width at 2 because there are 2 islands, and now it's 0 because I've removed everything. Okay, now I look at the maximum width seen during the play. So in this case, it's 2, and I want to minimize. So here I have a repairing and a way of erasing everything that only uses width 2. Can I reduce this to 1? Well, in fact, for this particular word, the answer is yes. But what happens in general, right? So what happens for if I have better words? Now, the width of a word is the minimum width of all its repairings, right? Of all such strategies. So here is a question. Do all words, and I'm thinking Duke words, have repairings of bounded width? So is there a magical constant, let's say 2020, such that all Duke words have at most this width? It's a very tricky question, and in fact the answer is no. You can prove that there is no such constant, but we don't really find any easy way of showing this. So how to prove lower bounds on the width? So what we do in this work, we show that there are sequences of words where the width is unbounded. So there is a sequence where the width tends to infinity. So there are words that really require large width. But then we also show that if you have lower bounds on the width, for some words, doesn't really matter for which words, this will imply lower bounds on NFA size. And the lower bound will be on the form n, basically to the power width of the word. So in this word doesn't really have length n, it has length at most square root of n, but that's a small technicality. Think about this. If you can prove unbounded width, then you can prove super polynomial bounds on NFA size. So let me tell you a little bit about these repairings, because proving things about them is difficult, and this is really what our main paper is about. So first of all, if you start with some word which is balanced, so Duke word, if it has length n, then it has a repairing of width log n. And this you can do by basically divide and conquer. So this repairing actually is simple. You always pair up matching signs. So that is signs that are matched with each other, as in balanced parentheses. So if you restrict yourself to simple repairings, to this property, then actually it's easy, well, not difficult, to compute the optimal width up to a multiplicative constant. So let me illustrate this. So if you think about Duke words as trees, you can kind of associate the structure of this kind of balanced parenthesis with a tree. If you have complete binary trees, then basically the optimal width is kind of the height. And then more generally, if you have an arbitrary binary tree, then you look at the largest binary tree somewhere inside. And this is something called the Strahler number, or the tree dimension of the tree, and that will be the answer. So it requires work to establish this, and there is a nice connection with black and white pebble games due to Lengauer et Arjern, but that is actually insufficient. This is a restriction. This restriction to simple repairings is actually quite, well, restrictive. In particular, consider a complicated word W. If you put it into kind of this framing of many pluses at the beginning and many minuses at the end, then you can repair such a new word quite easily, as long as this K is big enough. How do you do this? Well, you start kind of reading the symbols of W left to right. If you read a plus, you pair it up with a minus from the end. And if you see a minus, you pair it up with the first plus here, or maybe the last plus. And then you kind of pair up pluses here with minuses here, and minuses here with pluses here. If you reason in this way, you'll see that the width of such words is at most 2, as long as K is big enough. But then W itself can be very complicated. So what this tells you is that somehow this restriction to simple repairings cannot do this. So somehow for simple repairings, if W is complex, there is no way you can trick this. This is a hard word. But if you don't have the simple restriction, then this is a very easy word. So repairings can be very, very tricky, and proving lower bounds about arbitrary repairings is more difficult than proving lower bounds against these pebbling games that I mentioned on the previous slide. So in fact, if you have binary trees of height n, I mentioned the simple big O of n upper bound. In fact, we can improve this to 2 to the power square root of log n, which is basically better than square root of n, or this thing is better than cube root of n, and so on, and better than any n to the epsilon. But this is not quite log n or not quite polylog n. Anyway, this was an aside. The important thing is that simple repairings are very difficult to reason about. So what we show is that there are words that require length, basically square root of log n. And you can think of the length of these words is square root of n as well. And then we show that this implies lower bounds of NFA, on NFA size. So this is the width, and you basically plug it in here. So both parts here are non-trivial, and I will not really talk about techniques much, except that I will talk, for now, I will mention the work by Brigitte Rozoy from the 1980s. So she showed that the Duke language, like Duke 1 language, is not EDTOL of finite index. So and the proof implies non-constant lower bound on width, basically. But then for complete binary trees. But unfortunately, this proof didn't really work. So it's published, but it has a mistake, and we don't think it can be fixed. So, but somehow this work inspired our constructions, although the strategy that Rozoy used didn't really work. So to sum up, our main results are lower bounds on the width, and then as an application, we have lower bounds for this transformation from OCA to NFA for the Parik image. Let me emphasize that lower bounds for the size of NFA are very difficult to get in general. And in this case, it's actually not a single language. We need to prove lower bounds against any language with the same Parik image. So future directions, there are questions about the width of the word that remain. There is a question of whether we can recover the proof of the statement by Rozoy that the Duke language is not EDTOL of finite index. And then there are questions about transducers that kind of generate Duke words of length n and don't generate any non-Duke words. So this is something that's related to Rozoy's work, because these models of computation are related deterministic to the two-way deterministic transducers. Thank you very much for your attention. I look forward to your questions.